Hey everyone, this is the code presentation for the paper Faster Projection-Free Online Learning. This is joint work with Elad Hazan from Princeton University. To present our work, I'll simply deconstruct our title and explain what it means to be online, what it means to be projection-free, and also how can we make this thing faster. All right. One could ask this simple question: what does online learning mean? We want to just say that it means handling everything on the fly, the data and the predictions on the fly. An example could be weather forecasting. For each day, we need to say rain or no rain. And statistical learner usually would just gather a bunch of data, assume that this data is representative of the future data, and get a hypothesis that they hope is going to do well enough on the future data. Usually, you need a distributional assumption in these cases. For example, IID data assumption. On the other hand, the online learner simply predicts every day something new. This allows the online learner to be both more flexible and also more robust. In this case, one doesn't need any distributional assumptions on the data, and the online learner can adapt to any kind of changes in the data that one might see. Okay. More formally, the general setting for online learning is as follows. It can be looked at as a game between a player and an adversary. And the player at a round T chooses an action from a constraint set K, while the adversary at the same time reveals the loss function Ft. This could depend on previous choices and the algorithm and everything. It's an adversary, so it's given all kinds of access to information and computation. The loss that's suffered is ftxt, of course, and the performance metric is regret, which is pretty standard in this online learning setting. Some typical assumptions that we would like to mention are that usually the constraint set is set to be convex and bounded. The loss functions are usually convex on Lipschitz. Also, the player is assumed to be given a gradient oracle for the loss functions, as well as an optimization oracle for the constraint set K. All right. So we got that out of the way. We're moving on to the second part of the title, projection free. We want to motivate why we're looking at the projection free methods. To do that, we'll contrast with projection-based methods. And projection-based methods basically allow for the possibility that potentially one could move outside of the constraint set in constraint optimization, and then one needs to project back to the constraint set and use this projected point as the next point of the learning. On the other hand, projection-free methods use linear optimization, and they try to stay inside the constraint set. This works more like you choose a point on the, you choose a direction to move towards to, and then you move a certain amount in that direction so that you never go outside of the constraint set. One prefers projection-free methods over projection-based methods, usually when projecting, which is quadratic optimization, is much more expensive than linear optimization for that constraint set. This is true, for example, for matrix problems and many other problems. To contrast these two settings to each other, two different types of methods, we know that in offline and stochastic cases, both projection-based and projection-free methods kind of have the same results, more or less, but there's a huge gap in the online adversarial setting, and this is what we're trying to tackle. To be fair, the stochastic result for the projection-free case holds for smooth functions, while the other one, the projection-based one, does not. But still, we're trying to tackle the gap shown over here. The lower bound in general for online optimization problems, online learning problems, is root T. One cannot get lower than root T regret if we're talking about general convex losses. And online gradient descent, which uses projections, actually gets this root t, and it's optimal. But in the projection-free methods, the best method is online Frank Wolf, which gets t to the 3/4 regret, unfortunately. And the optimality of it is not known, whether this is a tight bound and we need a better lower bound, or whether this lower bound is tight, the general one, and we need better methods, is not known to the community. We would like to note that for the projection-free methods that we're looking at, the oracle complexity is key, because abusing a linear optimization oracle would lead to just simply being able to compute the projection. If I'm allowed too many linear optimization calls at each iteration, then I could compute the projection and imitate OGT, get root T regret. So what we do is we restrict to constant, or say one linear optimization call per iteration for our methods. And finally, to touch upon the smooth versus non-smooth rivalry, the non-smooth case is usually the way to go for online optimization. Most of the time, the smoothness assumption is not really useful for this method, so all of the results hold for non-smooth loss functions. However, for projection-free methods, most of the results are for smooth loss functions. Smoothness is pretty important for the projection-free optimization setting. We know that our result actually improves the t to the 3/4 regret to t to the 2/3, but in the smooth case. So our result holds only for smooth convex loss functions. Next, let us state the algorithm we propose and its regret guarantee. The algorithm is sampled FPL, or the main algorithm that will say what it is. They're pretty related to each other, and sampled FPL refers to follow the perturb leader, a widely known method in the online learning literature. And what we call sampled FPL is at each round simply computing several samples, k samples of FPL, and playing their average as our point, xt. Our main algorithm, because we restrict to one linear optimization call per round, we wait for a while to accumulate linear optimization calls. We cannot do this every round, so we wait for kt to the 1/3 rounds, and then we compute the k samples of FPL, just like sampled FPL, play their empirical average as before. And this is the algorithm that we refer to in this work. The regret guarantee for this main algorithm, we just described this as follows. The assumptions are k should be, the constraint set should be convex and bounded, and our functions should be convex, Lipschitz, and of course smooth. In this setting, our main algorithm uses only one gradient oracle call and one linear optimization call each round, and it gets the t to the 2/3 regret, which is an improvement, as already said, upon previous work. To see why our algorithm works and how to analyze it, we'll just touch upon some very known things in online optimization, and also how to use those things for projection-free methods. The two main methods that are all over online learning literature are regularized follow the leader and follow the perturb leader. Regularized follow the leader is this method that uses strongly convex regularization and the past actions as well as the feedback to compute the next action of the algorithm. It's given as follows. And it can be shown that this achieves optimal root T regret. One would think that to design a projection-free method, we could try to imitate this, and instead of, because this is a strongly convex optimization problem, just use the linear optimization calls and get something close enough to xt, this xt hat. However, it requires us to use T calls to the linear optimization uh, oracle to get root T regret, and this is equivalent to the T to the 3/4 regret. This is basically the starting point for the online Frank-Wolf method. There's a lot more to it, a lot more technicalities and subtleties, but basically this is how one would go about deriving a method that would get T to the 3/4 regret. And we already mentioned that this is the best known regret in this setting. So we're not going to take the same approach in order to get an improvement. What we do is we look at FPL. FPL, on the other hand, uses randomized regularization. It's linearized into linear regularization. However, it's randomized. The V is random, is a random vector here. And it's widely known that this gets root T regret for linear loss functions only. It can also be shown that if you use expectations over the FPL points, as here, one gets the same root T regret result for general convex functions. The great thing about this is that we're using linear optimization as a building block already, and that's great for a projection-free method, right? The bad thing about it is that there's an expectation here, which is not tractable, obviously, and using estimation with samples gives us more randomness. That's hard to tackle. The randomness in online algorithms is notoriously hard to analyze, as well as, more importantly, even if we get by all those issues, if I'm going to get an estimate that's 1 over root T close to this xt point, the expectation, by concentration inequalities, I need T samples. I need T linear optimization calls again, which was the case for the previous RFTL approach. So in this case, it seems like, again, we come back to the same T to the 3/4 regret, and there's no improvement. However, in this work, what we actually show that better analysis approach, a better analysis framework can lead to having the same exact method, but having an improvement upon the previous best T to the 3/4 regret. Okay. Like I said, we use a different approach to analyze the online algorithms, and it's called online primal dual framework from previous work. This is a known approach, however, it has not been used to improve any results in the community. So in this approach, you take the primal to be more or less the best loss in hindsight, and the idea is to choose an action that would allow us to bound the cumulative loss by the dual. And then, of course, the dual is bounded by the primal by weak duality. And this approximate part would basically be the regret that we achieve. The benefits of this framework are that there is no error accumulation. We get separate regret for each run, so we have no issues with the additional randomness, with the estimation error. There is nothing that gives us a hurdle. And on top of that, the extra regret term allows us to bound it in a clever way using the smoothness of the loss functions to actually get our improvement to the T to the 2/3 regret. Basically what this gives us is with K root T samples, the sampled FPL gets root T regret. And to summarize our paper is we can say that for convex and smooth loss functions, we achieve root T regret with overall T to the 3/2 linear optimization calls. Our reduction with 1 linear optimization call gets T to the 2/3 regret. Additionally, in the paper, we show that these results hold with high probability. The variance is not too big of our results. It's not just the expectation that holds. Additionally, we want to note that there is a dimension dependence due to the FPL method that needs to be tackled as a future work. Also, that future work could also include optimality answers about online projection free methods that are again still unknown. Thank you very much.